Hello, everyone. Welcome to the Synopsys tutorial session at DVCon 2022. My name is Kiran Vittal. I'm responsible for verification software solutions at Synopsys. I'm based in Mountain View, California. As you can see, the tutorial is for 2 hours, and the title is Your Hardware Dependable? Practical applications for managing security and safety from software to silicon. We have lined up experts from the industry, from DARPA, AMD, ARM Research, and Synopsys. The first speaker is Serge Leef from DARPA. The title of his presentation is Practical Strategies for Managing Security in Silicon, followed by Bala Chavali from AMD. Her title is SoC Functional Safety Overview and Use Cases, Standards, and Dependability Lifecycle. The third presenter is Reiley Jeyapaul. Balaji Venu has also contributed to this presentation, and their title is Reliability Analysis Method for Safety Critical CPU Designs, PACE. And last but not the least, we'll conclude this tutorial with a presentation from Meirav Nitzan from Synopsys, and the title of her presentation is Automated Solutions for Safety and Security. So as the presenters are presenting, please feel free to submit your questions through the chat window, and we will take up the questions somewhere along the way or maybe at the end of the tutorial. So thank you once again for attending. I'll then hand it over now to Serge Leef to start his presentation. Thank you all.
Hello, my name is Serge Leef, and I'm a program manager at DARPA, focusing on secure silicon, next generation design automation, and domestic microelectronics. So today, I'd like to talk about the practical strategies for managing security in silicon. And this is a topic that's near and dear to my heart because my group at DARPA has been focusing on this very issue. So the goal that we have been pursuing on my DARPA team is essentially around automation of inclusion of scalable defense mechanisms into chip designs. And the reason for doing this is to enable security versus economics optimization and pursuit of trade-offs. So the principal observation is that there is not one security strategy that fits all cases. And so what we're doing is we're sort of looking at this as a gradient of security strategies and corresponding costs. Like, for example, if you put a lawn sign in front of your house that claims that you have security system installed, that is perhaps sufficient to deter some of the potential security threats. But then on the other hand, on the opposite extreme of this, you can have Fort Knox level security, and that still may not dissuade some types of highly committed attackers. And so, so basically, the way that we are thinking about this is that security really needs to be incorporated into modern design flows. And the reason for that is that it needs to be connected to multiple structures at the architectural and microarchitectural level. And one way that we think it's possible to do this is by use of the platform-based design strategy, where you have a number of parameterizable IP blocks that come together in a platform, and that can be configured in a variety of different ways to achieve different goals. And so system on chip design process obviously is not anything new, and it is something that the design automation industry has been trying to address for a long time. And even the most simplified versions of design flows that people use today sort of look like this. And so current practices are, to take a bunch of IP blocks, to manually integrate them, to simulate everything, and to then perhaps original design content kind of one at a time. And the idea is that that you can a human can create an infinitely small chip with implementation with infinitely fast performance, but the reality is a human expert with unlimited time can only come so close to that goal. And so when synthesis emerged in the 80s, late 80s, it basically showed us that the machine can generate multiple architectural solutions, but they do not necessarily represent as good a job as a human can do, but over time they become better and better. And so this is basically led us to the current state of affairs in chip design, where low complexity SoC costs about $30 million to design, and it takes 9 to 12 months to design such a thing. And many human errors are introduced in the process, but significantly security and power are not massive considerations in this. Certainly security is not. And so the long-term dream of EDA industry has been to synthesize the entire SoC. And that's sort of where we get into this conversation. So why not revisit system-wide synthesis? And historically, the optimization was on performance versus size continuum, but that clearly is outdated already, because now we need to consider power as another element in this equation. And furthermore, as we're talking about security, security needs to be contemplated here too. So now we have increased the number of domains on which we optimize. But if we further dissect security into subset of attack surfaces, then you see, oh, there's more than one attack surface. And so now we have really complex multi-dimensional synthesis and optimization problem to address. And the key challenges here are security is very hard to quantify or model. How do you estimate degree of resistivity to attacks of one architecture versus another? And how do you optimize on 4 to 7 dimensions? Those are big questions. So before we get to those questions, we start thinking about, so what are the attack surfaces that we are interested in? And we see that there's a lot of activity on the software side where people have been dealing with cybersecurity there. At DARPA, we have a program called SIF, where we focused on hardware-software interface. But here in my group, what we're really doing is focusing on the hardware security. And here, the attack surfaces that we are pursuing are side channel attacks, which is extraction of secrets through communication interfaces other than the ones intended. And we have to make a conservative assumption that attackers are able to hear what the chip is emitting. Looking at reverse engineering being the second attack surface, and this is where an adversary wants to extract algorithms from illegally obtained design representation. Again, pessimistic assumption here is the attackers have access to the design files. And then the next attack surface that we worry about is supply chain attacks, where you have cloning, counterfeiting, recycling, remarking of chips that are subsequently represented as genuine. And the assumption we have to make here is that the attackers can manufacture perfect clones. And lastly, the last attack surface of interest is malicious hardware. And that means insertion of secretly triggered hidden functionality into the designs that can be triggered or activated later. And here we have to make an assumption that the attackers have already inserted malicious functions into the design. And the question becomes, so what do we do about this now? So who are we trying to help with this technology, right? If you sort of look at the parties that design chips today, you see huge merchant semiconductor companies. For them, security is actually very much a central question, because it ties to business factors like revenue and liability. And so those companies have large teams of people that create custom security strategies for their high volume silicon. Then you have the mid-sized semiconductor companies and system companies that do ASICs. And here you see that either they have lack of expertise or insufficient economic motivation to do anything about this. You go to defense contractors, And now you see, yes, they have expertise, but it's applied very unevenly. And this expertise is treated more like craftsmanship as opposed to engineering. And lastly, we have system integrators. These are people who build vertical solutions like intelligent door locks, for example, security systems, lawn sprinklers, various other connected household appliance, essentially IoT based integration. And they really typically don't have interest in security because they're trying to hit tight market window, and they would rather invest in things that would help them sell their products. And so here, the people we're trying to help first with this initiative that we are pursuing is the parties in the middle. And then if we're successful, we think we can also appeal to the large merchant semi companies by saying we can reduce effort required from you on future designs, and we can make a reduced cost argument to the system houses. In other words, security is already there, comes at no cost. Why not make things that are secure rather than not secure? And so the central element of what we're doing is the notion of security engine. And so in this context, what we are essentially doing is we're introducing this piece of IP, which is largely hardware, but also has software. And this piece of IP resides inside an SoC and effectively protects against attacks through those attack surfaces that I've discussed already. And in each case, it could be more or less functionality depending on the importance of a particular attack surface. And obviously, there needs to be some off-chip support here, and because this type of system needs to interact with the outside world to track, authenticate, provision, etc. So in this program that's called ACE, Automatic Implementation of Secure Silicon, we are sort of following phases. We have 3 phases, and in phase 1, what we're doing is we're bringing together a bunch of IP blocks. Some of them are general computing and control, and some are security related. And in the first phase, our performer teams essentially are creating assisted composition, where all of this IP blocks can be thrown together. Bus interface logic is generated. Necessary device drivers are produced to tie all of this together. In the second phase of the program, we do automated composition, but in a different way. Now, our starting point is a platform, and this platform has multiple parameters to choose from. Like, for instance, there may be several types of CPU that are available in the platform, or different communication protocol engines. And so an engineer in this case would make selections of the blocks that of the parameters that are important for this application, and then we automatically generate this integrated platform connected to a security module. And ultimately, in phase 3, which is the final phase, what we want to do is we want to move to the point where simply the cost function is specified. And here we're going to say performance, how important are performance, size, power, and security, and then further provide texture as to what attack surfaces on the security side are important, and have optimization engine produce a huge number of architectural solutions and maybe choose the ones that are the best for the human to take a closer look at and to determine whether or not this cost function that we've established, which has performance, size, power, and security, is actually satisfied. So how do we do this? The optimization strategies have really been experimented with in the 80s. And so an example of a strategy here could be combinatorial optimization. And what we would then look at is how do we parameterize different applications? So for example, you can look at lawn sprinkler and say, okay, performance is not all that important. Size is important because that translates to cost. Power is important because this is supposed to run on the battery for a long time. Security is not important. But if we take a closer look at security, we see that, oh, you know what, maybe supply chain security actually is important here, because we do not want the situation where this thing gets copied and then saturates the gray market, taking opportunity away from the sales of this particular company. So where we really want to get to is we want to get to the notion where security engine is something that's pervasive and present on majority of chips, but it is also sized in a way that fits the application needs. And then if we do have something like this, then we can essentially enable an entire suite of applications ranging from design time, where we can create, when we can figure out what parts of our chip we want to secure, provide unique identity, inborn root of trust. And then this will allow us to follow each die through the process, where we can have intelligent enrollment. We can configure individual die. We can provision individual SKUs downstream and manage inventories better and repurpose parts if we have to, when markets we anticipated don't pan out and others do. We want to be able to authorize various parties to manage security structures. And we want to be able to securely update firmware and monitor operation of these things in the field. So with that, I will conclude my presentation and say that I enjoyed speaking here, and I look forward to the questions.
Hi, welcome to DVCon. My name is Bala Chavali. I'm with AMD. Today I will be talking about SoC functional safety overview and different use cases, how this is part of the dependability lifecycle, and different standards and working groups that are working on this right now. So let's get started. First, I will provide you a brief overview of a dependable system, followed by product hierarchy and the different layers within a product. And then we'll talk about, within a specific layer, what are the different life cycle phases, and specifically the functional safety attribute, followed by SOC and dependability life cycle challenges, and how we're addressing these different challenges with the industry, as well as different working groups and working groups. So first, what's a dependable system? Trustworthiness of a system. It's that the user has a need for a desired behavior, along with confidence that it will work, and that it will. And here, the system could be a car, manufacturing facility, dishwasher, essentially most of the electronics that we use. We specify specified attributes to measure this dependable system. The quality of this dependable system could be measured, qualitatively or quantitatively. So here in this figure, you can see that the dependability attributes are reliability, functional safety, security, availability, maintainability. Now, security also includes, confidentiality, as well as integrity as well. Each and every one of these attributes have their own metrics, have their different measures. Now, we have ways these measures, allow us. We implement different measures. For instance, for functional safety, we have, safety mechanisms, right? We could implement more safety measures depending on what our targets are, which allows us to increase the system's dependability. So there are ways that we identify what are the different attributes, and also identify what are the different where we could have gaps. And finally, we actually will increase. We could increase the system's dependability by adding different type of measures. Now, each and every one of these attributes have their own life cycle, have their own phases, have their own work products and milestones. Now, when you have one attribute along with a product life cycle, you go through every one of your different milestones within the product, and then you make sure that all of the target and the work products for that one attribute is, has been met and has been completed. Now, when you have multiple of these attributes, that are part of a product lifecycle, we start having different challenges. So again, there are different standards and industry working groups that are also working on, trying to create that uniform view, create that holistic view that includes all these pieces, so that we will be able to make these challenges much more easier to be, we can reduce these challenges. Therefore, our product life cycle and our product development would be much more easier. Now, as we said, there are multiple different type of systems. A car is one example of a dependable system. Now, I'm just going to use an automotive application to walk you through what are the different hierarchy layers within that, and what are the different life cycle phases, so that you are able to go down further deep. Now, as you can see here, the vehicle, from an automotive point of view, you have multiple layers. You have a vehicle, all the way to a system module, component, down to an IP. When we have requirements such as, which of the attributes of the dependable lifecycle will be applicable for the vehicle, these will not just be at the top layer. We will be rolling these requirements all the way from the vehicle down to the IP. So if we have a requirement that says this application requires functional safety, we know that we will specify a safety goal, and the safety goal will be fanned out all the way down to the IP, to the SoC, to the block. Same thing with security or with reliability. Each and every one of these attributes become requirements that will be worked through the different layers within the product. Now, automotive applications, really require us to look at most of these attributes. We talked about functional safety, which really targets to reduce risk in critical applications. Most of the applications here require some type of functional safety goals. Where we have functional safety goals. We also have reliability piece, that's also needed for automotive applications. And it's really, for the error avoidance and making sure that we are able to detect, along with, wear and tear, aging, and so on. And there's also, different type of security needs and requirements that go here, so that we can, go address the different threat levels as well as attacks during the product operation. This is just to list a few. It's not, intentionally, the maintainability as well as availability is also needed, but some specific applications have the specific needs. But this is just to highlight a few. Now, as we go, we talked about the product. We looked at the different layers within the product. Now, if you pick a specific layer within the product, which could be an SoC, which is a component, each of those layers have their own life cycle, meaning that you will have to start at the definition. You gather up your requirements, you convert that into architecture, you go do a design, you go build the design, follow through the implementation, design and implementation, and then you go test, verify, validate to make sure that your what you specified is, how it's working. Finally, you go through production, operation, and decommission the part. So start all the way at the definition, and you take it out. The product is shelved. So from the start to the end. So all these different phases within the life cycle of one different layer, could be described, could be shown in different ways. It is pretty common to use a V model to represent this life cycle. I'm just showing here in this figure, sort of a flat hierarchy of what are the different stages. Now, dependability attributes that we talked about earlier, functional safety being one of them, security being another, these attributes have their own life cycle, which we have to integrate as part of this product life cycle. Now, each product, as we talked about earlier have these requirements that come from the top layer all the way down to the other layers, down to the IP. The product will define set of requirements, and that each of these requirements, whether it's on the attributes, those requirements have to be fanned down. Now, the product will also specify the different qualitative and quantitative targets that need to be met. Now, just as we just look at it, when we talk about functional safety, we'll have safety goals. The safety goals will be specified at the product hierarchy, and within the layer, the SOC will say, okay, these are the safety goals for this project, for this product, and that we need to achieve them. There could be quality targets, there could be reliability targets, and they will be having maintainability, as in how do we repair, and what is our ability to repair, and how many times do we need to repair. So within a product, we have multiple life cycle. We have multiple life cycle phases for the SOC. Now, as we sort of started looking at an SOC and we looked at multiple life cycles, one of the attributes that gets overlaid on top of the product life cycle, for instance, could be functional safety life cycle, right? So as all of us are very familiar with functional safety, there are multiple standards that are there for functional safety. They provide those guidelines and recommendations on safety management, product management, as well as risk mitigation for the product throughout the life cycle. They address this via two methods. They talk about the random faults, they talk about the systematic faults. And as we look at just a bit more into the random faults, here we go get the architecture, we go get the design data, we apply the safety measures, we perform the safety analysis, and we evaluate if our safety goals have been met. And we look at the safety metrics and we say, okay, the product goals have been met. That's on the random side. Now you have on the systematic side. As we go through those different life cycle phases that we looked at earlier with product definition, we start over there where we say, gather up the different requirements, customer requirements, the different product as well as market requirements, and we take them and we go specify a product specification. We go create a product specification. Then we define the architecture, we go build, and we test the different components. All of this, we do this systematically. With the traceability, we have different design and test methods to avoid those systematic faults. Now, all these different requirements, all these different metrics that we have, all of them need to be connected back into the product lifecycle, so that we know that yes, the goals have been met. Yes, it's not just the quantitative part, but the qualitative part, that all of them are in place. Now, how does this sort of tie in, back into the SOC, and what challenges do we get when we just take one of these attributes, one such here being functional safety, and we connect it back into the product cycle? So as we look at the definition and the design phase specifically of an SOC, we know that we go figure out what are the different IPs that need to be present within SOC. This SOC could have multiple internal blocks, or it could have some third party or external IPs as well. As we start building up the internal IPs, we go gather up the requirements, we go create a definition of these IPs, and then as part of the definition of the IPs, we'll be creating, we take our requirements, we go publish them, we convert our requirements into architecture, we get the design to be implemented, and once we have the design implemented, we get it reviewed, sign off, and finally we also establish traceability to make sure that what we intended is the behavior that has been implemented as well as tested. The same is true both for internal blocks as well as any third party or other IPs that that probably are part of your design as well. Now, when you have this combination of internal external, you also have to make sure that both of these IPs are able to talk to each other. So there will be some type of checks in place. You want to also make sure that you have documentation that would be able to, you have documentation that you would be able to connect the IP so that when you go through integration, the design works great. So as we look at each individual of these IPs, they work. But when we start actually integrating them, when we start connecting these blocks with each other, there could, we could start seeing different challenges. One of the challenge usually is data exchange format of requirements from one IP to another IP, from one IP vendor to another IP vendor. And really, this is when we start looking at different data exchange formats of requirements, sometimes we start noticing different type of feature gaps. Now, feature gaps could be that the IP standalone works, standalone is able to, works great. Now, when we start connecting them, each of the IP need to be worked under specific conditions, and that might not have been synced with the requirements of one block to the other block. Now, standardizing, what would be the way to address this challenge, right? So standardizing is spec format, using requirement tools to capture the requirements, so everything could be imported and exported between these different IPs, so that there is no manual work there. And this allows to really get the traceability piece, as well as it allows us to not have any gaps, right? So that we are sure that the data exchange, as well as all the information is present, and that we have marked it complete, because you're making sure that every one of the items have been covered. Now, one of the other challenges that I've commonly seen is integration challenges due to non-standard design or custom methodologies. Really, I think standardizing design deliverables and have the ability to run, different scripts to identify errors, or, creating common terminology of ports and auto-generating really helps, this set of integration challenges. And finally, another challenge is lack of common terminology or language between different databases and users. This is a challenge because it's not something that one individual can address it. It's something that this is where we require different working groups, industries, to come together, to gather up the different requirements and to create that coherent view for everyone, so that we know that all the different use cases are present, and that we are able to make sure that the different requirements, whether it is the different formats that each database or each different unique tool is talking, is able to not just share with each other, but also understand that they both have the same meaning, they both have the same definition. And all these challenges at the end results, having those challenges at the end of the day results in higher effort, spending more time, the product delay, and by having different requirements, or misinterpreting or having those gaps, with the requirements at the end of the day could create bugs, and therefore cost additional time to debug and to get it fixed. So this is sort of the challenges that we have within an SOC, within the life cycle. Now, when we look up to the product where we have multiple layers, and not just multiple layers, here we now have multiple attributes, the challenges actually multiply. Especially when a product has to address multiple life cycles with multiple attributes for one single product. So here we're talking about, back to that automotive example, you have automotive application where I need security, I need functional safety, I also need reliability. I have different standards. And on top of having different standards, I also have different, I have to make sure that my one single product, which is targeting all these different attributes and life cycles, make sure that all of the milestones and all the gates are present and all the different targets have been met. So, I think having management that understands the complexity of this, and making sure that the different gates have been set will really allow us to, first understanding that the challenge is present and having a team that understands what are the challenges and why those challenges could be erased is the first way I think this challenge could be addressed. Now, the next one is, that we have to comply to multiple standards and produce multiple work products. And this is there for sure there because when we talk about functional safety, you got some amount of different standards. For security, you have another set of standards. Each and every one of them, require you to generate different set of documentation, require you to, look at, at the definition phase, they want you to look at certain type of requirements, and being able to make sure to map each and every one of those requirements as part of the product lifecycle, becomes very important. And having this one, along with the next challenge being all of these different attributes, they use a similar data set to perform their quantitative and as well as their qualitative analysis. When we talk about similar data sets, we know we have to perform, safety analysis. We got risk analysis. We got threat analysis. They're using the same data set. They are using the design data. They're using the different type of measures that you have within your system. They're using different type of safety mechanisms. They're looking to see what are the different type of failures that could happen and that could be propagating from one level to the other. So there is, we have common set of things that are shared within these different attributes. Now, how we use the data and what type of analysis we do is different for each and every one of them. And so therefore, having the ability to sort of have a database or have a data model that allows us to bring that entire data set and make sure that we're able to provide it and make sure that we're able to generate the output would be great. But right now, most of these different data sets are sort of looked on individual basis, and that just sort of adds up to the effort. So you need multiple different individuals to be able to do each and every one of this analysis, and it also creates complexity into the dependability lifecycle. So this, I think, the last challenge is a bit more, tough one to address, and it requires again the industry and the working groups to come together to create that uniform model, so that we are able to get the inputs, and we can create a model that would be able to that could be leveraged and used by everybody. So how are we addressing these challenges? Really, there are different experts that are working together as part of working groups to address them. The first one, being just the dependability lifecycle part that we talked about, is to define a generic dependability lifecycle that includes all those different attributes. And once we identify what are the common pieces between them and what are the individual unique ones, we would be able to make sure that we can group, the common pieces and the other ones that require additional, a set of steps. The second one is to identify what is that holistic data set. We talked about different analysis pieces earlier, and being able to find, what is the full data set that is required by all of them, and then create the analysis is another one that's also, that needs to be looked at. Finally, it's to create that common data exchange language. We talk about, design data, we talk about flops, some teams talk about, gates, and some other person might talk about, the technology gate. So each and everybody has their own different terminology, have their own different language, but having that one common data language allows this data exchange and these databases to be able to exchange data easily, and it doesn't leave any misinterpretation of the data set. And all of this, because here we have automotive, industrial, avionics, medical, all of them have the similar type of requirements. So going across all these different markets, across the different layers, we would be able to bring multiple of these different applications to create this. And finally, the last but not least is to promote interoperability between the different tools. And this allows us to, once we create that data model and databases, once that common language is established, then you can go from one IP, one vendor, one tool, and the same data set could be leveraged across a different tool. All of these challenges are great, and as I mentioned, some of these challenges and how we address them could be are done within our teams, within what we work on a day-to-day basis, whereas some challenges require us to come together and to solve them, to understand them better, and to create the common language. So finally, there are, as I mentioned, there are multiple industry working groups that are happening, two of which that I've listed here. One of them is the Xora Functional Safety Working Group, which I'm also a participant of, and they are working towards defining a standardized functional safety data exchange language. They're also defining language in different formats to exchange this different data set that I mentioned earlier. And finally, they have released a white paper highlighting all these different challenges, as well as the ongoing work and where the data model work is happening right now. Now, there's another working group, the IEEE P2581. They also published a white paper, and they're working towards the data exchange, but also creating this dependability lifecycle that encompasses all of these different attributes, so that we can have that uniform as well as that holistic view of all the different aspects. So today, I gave you a view of what is the dependability lifecycle, along with a specific hierarchy layer, and within the layer we talked about the different lifecycle phases, and the lifecycle phases and the challenges that sort of come in as we work on a specific component, and how those different challenges are being addressed right now, whether it is within different teams or with the industry. So thank you very much for your time today, and have a good day.
Hello, everyone. My name is Reiley Jeyapaul from ARM Research. In this session, I will talk about BASE, methodology we developed using formal tools for fast, accurate, and scalable reliability estimation that enables a reliability-aware CPU design cycle. We will start with talking about why we need such a methodology, talk about the methodology in a bit more detail, some results, and then I'll present a simple example use case within the ARM ecosystem and business model. Functional safety is required across multiple market verticals. Some of them are very established, such as industrial, transportation, and avionics. Others are more nascent, such as consumer and medical. Automotive is, of course, a key vertical for ARM, but we look to scale across adjacent markets with our safety solutions. In that direction at Research, we were looking at this problem of error-resilient system design. And when we look at it, we understood that an implementation of fault tolerance is nothing but a mechanism that introduces or enhances the intrinsic masking effects of the design. In addition, in order to enable that, we need to be able to accurately analyze the vulnerability of the design and also quantify the failures of the design. So if we put these two components together, we achieve what we call as a reliability-aware design loop. So a designer can quickly analyze for the vulnerability, estimate failures, and then with that feedback, be able to optimize the design and then quickly check it again as a loop instead of having to mature the design before failure estimation. This allows for some efficient co-design, efficient and smart innovation in fault tolerance. And in addition, this also scales well to larger designs. So while looking at reliability estimation methods that would help achieve this reliability-aware design loop, we started exploring the landscape. And what we have is fault injection experiments, which on RTL or architectural models have this cost of time. There you have to run numerous number of simulations before you get a result. On the other hand, if you have analytical models that you have to run only once, are abstracted and therefore lose on accuracy. In our methodology PACE, what we intend to achieve is a gap, is a bridge between these two that enables analytical models of ACE on RTL and with limited trade-off in accuracy and speed. So ACE is a common technique used in estimation of AVF. It involves some pre-analysis of the CPU structures. We're looking for their behavior as a functionality. And in the presence of data accesses, you can either deem a particular component as ACE or UNACE. ACE meaning if it carries values that are used or consumed by the system, and UNACE if those values in the bit is not going to be consumed and therefore are not vulnerable to transient faults. In PACE, what we do is we extend this ACE analysis on the RTL, and we've designed the same on as an example on the ARM Cortex R52 CPU. And using formal methods, we've been able to automate this whole methodology. In our experiments, which I'll present later, we've compared our AVF numbers from PACE against exhaustive fault injection experiments, which is we've injected one bit flip on every clock cycle on every flop of the design for a bunch of benchmarks. On together, we've run some 125 million independent RTL simulations and a huge terabytes of data. So what is this PACE methodology trying to solve? It's a methodology that we use to achieve two things for safety critical system designs in particular. One is being able to derate the fit of the CPU so that we can still achieve the fit budget of the system for particular set of applications. Given that PACE is able to achieve application based fit estimates, you actually have a methodology now that gets you a derating factor. And the other is you could enable some smart code design. You could do selective hardening. You could do selection of safety mechanisms based on the applications that are used in your system at deployment. So PACE allows these two by enabling fine-grained safety analysis. And all this is enabled through formal methods. So in summary and a nutshell, what we've achieved is a methodology that is 276 times faster than fault injection or exhaustive fault injection. The limitation is that the estimates using PACE are on an average 4.7x higher than that of exhaustive fault injections. And this is a pessimism that is inherent with ACE modeling. Using the formal methods, what this methodology is able to still achieve is two guarantees. One is the 100% confidence in the estimated AVF numbers, meaning any bit that is classified as vulnerable by the PACE methodology is also vulnerable by the exhaustive fault injection results. Again, you can use this methodology for fault space pruning because whatever bits are deemed as not vulnerable by the PACE methodology are also not vulnerable by exhaustive fault injection. The conditional vulnerability is the one that is a component of this pessimism, which we will see in a few slides. So the methodology. In a nutshell, the methodology is nothing but you guess and you check. So we start with using formal properties. We classify the flops in a given design as in one of three buckets: always vulnerable, conditionally vulnerable, or never vulnerable. And then we use sequential equivalence check to prove this classification as true. And if proven, we translate that directly into the bucket for proven buckets. And if not, we move them into the appropriate buckets. At the end result, we have a set of classification of the flops, of all the flops in the design, as either always, never, or conditionally vulnerable, and also the conditions in which they are vulnerable. And using this set of flops to monitor for data access behavior, we then use that in an RTL simulation to compute AVF of that entire CPU. In our results, we've validated this AVF number that we achieve using this methodology against exhaustive fault injection results. So let me go into some detail about some interesting components of this methodology. One very crucial component is the conditional vulnerable flops. So we evolved this methodology based on our understanding of the protocol of the producer-consumer handshake protocols that we see in implemented pipeline designs, and storage structures and some bus protocols. So what we see here is that if there is a flag associated with the payload, whenever the flag is valid, the payload also carries useful data. And whenever the flag is invalid, the payload does not carry useful data, or the other way around holds true. So using this hypothesis, we built a set of vulnerability hypotheses for all the flag payload that we can assume within a given design. So what we went about doing is we used system Verilog assertions to define this hypothesis, as we see here. And to start with, what we did is we listed all the flags in a given design by grepping for all the flags by the naming convention, and also some designer input to tell us which is which. And so now we have a set of flags. And then we assume that all other signals in the RTL are payloads. Now with this, we ran these assertions to see all possible combinations that would satisfy this property. So all these combinations that would satisfy this property are potential pairs that we can claim to say that they are a link. And what is the benefit of this? So while doing this RTL simulation, what we want to do is we want to be able to monitor a bunch of flags or registers for their data access behavior to see if they are read and written, or in other words, they are carrying useful data or not. And in order to do that, we use the flags as a signal to tell us if they are carrying valid data or not. And by monitoring the data's behavior of these flags, we are then able to compute the AVF of that particular payload for the duration of the application execution. So in the next step, we have to prove this, because we need a proven methodology. These conditional pairs that are potential pairs, by just grepping and matching them with the properties will not hold. So what we did is we used sequential equivalence check to prove this hypothesis and these properties that we've seen. So those that is used using this model that we see on the left. So what we have is we create a copy of the CPU, mutate the payload behavior on in the copy using assumptions, and then this is run, and in a sequential equivalence check run, what we've also done is we've assumed a fault injected in one of the copies to simulate the ACE behavior and to see if the equivalence is proven. And if the equivalence is proven, what we have is a proven model that proves the classification of something is vulnerable, or something is never vulnerable, or something is conditionally vulnerable. In more instances, this is particularly used for conditional vulnerability. So we have a proven conditional vulnerability here. If the SCC returns back with some violations, we know that the condition is not valid or some condition is incorrect. And therefore, we move that payload into the bucket of always vulnerable. In some instances, which is normal and formal methods, because of state space explosion, we see that it times out. And in that instances also, in order to be more pessimistic than have a false positive, we move that payload to be always vulnerable, and therefore, which adds to our pessimism, which we've taken some attempts to improve on, which I'll talk about in the later slides. So once we have this buckets of flops in these three classifications, we run an RTL simulation for a given workload. And for all the flops that we are monitoring, meaning all the flags that we are monitoring, we have a bit activity for over the entire duration of the simulation run. And now what we have is we have a temporal data access activity for the entire simulation run for those flops. Post-process on that using the ACE model, meaning whenever there is valid data, it is vulnerable. Whenever there is invalid data on a payload, it is non-vulnerable. We compute AVF of the entire CPU. And that is the AVF number that we use to compare and derate and as a metric for failure estimation. So the equation that we use to compute AVF is over there in the top left. The number of flops that are potentially result of an error, meaning that carry vulnerable data over the total number of flops at any point in time is the AVF at that point in time, and then accumulated over time is the AVF of the CPU for that simulation time. And the same is that for fault injection methodology. So the graph on the right shows results where the orange graph is that with PACE, the green graph is that with exhaustive fault injection results, and the blue is an improvement over the orange, which I will talk about in the next slide. So the interesting point to note here is two things. One is that there is an offset, and the offset is pretty constant, and the gap is around 5.1 over here. So that is the duration or the pessimism that is due to the ACE analysis. And what we also see is the correlation here. The correlation coefficient is above 70%, which is rather good, meaning what we see is that AVF calculated using PACE follows the trend of the exhaustive fault injection results. And therefore, the offset can be, in an ideal scenario, can be reduced to as minimum as possible, or the pessimism is also valid in some instances. So with improvements, we were looking at use cases, and one particular use case instance was in the decode unit, where we saw that the decode unit were exhibiting different behavior, and the PACE was unable to accurately capture the vulnerability behavior. And the reason was because the classification was we moved the unproven models, unproven flops into the always vulnerable bucket, and therefore they were always vulnerable, and so we saw a flat line on the orange. And this was because there was a circular buffer implementation in some instances, and whose vulnerability is not proven was not captured by the flag payload model that we have. And for that, we had to implement a different assumption and different hypotheses of the vulnerability. And when that was implemented, we were able to improve on the vulnerability estimates. So what this is an example of saying that with some designer input in corner cases for certain blocks in a design, if we are able to understand the mechanism and the functionality of the RTL, we can define assumptions that would still capture the vulnerability model and therefore close the gap between the blue and the green graphs. And this involves some designer inputs on legacy designs. But if you are to do the same for future designs and start this whole process of implementing PACE methodology right from the start, we can implement some design guidelines that would help with these classifications and reduce this gap in a design loop. So last, I want to present a use case where we envision the use of the PACE methodology within the ARM ecosystem as well as within our business model. So first, while designing our CPU and a system IP, the PACE methodology is automated. It is enabled using formal methods, and therefore, with the current infrastructure, we can automate for a given CPU and a system IP. We can automate these PACE models that would enable an RTL simulation for the IP that we deliver to generate AVF numbers, and all of this can be automated in a single push button solution, and this can be licensed along with our safety package. The next model is at the partner's end. So where they take these PACE models and they build their whole SoC along with our cores. They have the PACE models for the particular cores. And what they do is they integrate these PACE models for the cores along with their existing simulation or emulation platform. They have the set of applications that they would target for their particular needs. And that would help them derate the F-safe or the fit of the CPU using these PACE numbers, and therefore get more grounded or more realistic fit numbers that would benefit their SoC fit estimates. The other thing is that these PACE models can also be compiled with our cycle models that are again licensed along with our CPU and system IP to tier 1s and OEMs that could also benefit from the same kind of methodology. What is also something to note is that in addition to automotive, this methodology is not specific to just automotive. It's specific to any design of the CPU that has functional or has reliability as a key metric. And in growing, as we talked about earlier, as we scale the use of functional safety and reliability, there are markets like cloud and HPC where this is of predominant need. And in those instances, this PACE methodology can enable some smart and more efficient safety mechanisms, more efficient reliability or hardening or protection mechanisms that would still achieve the kind of reliability that is needed while not paying the cost of over-design. And so for PACE methodology is an automated methodology. It is powered by for formal tools, and it is fast. That would enable a reliability-aware design loop. And this allows us to, because it is proven using the sequential equivalence check, we get AVF numbers with 100% confidence. The fine-grained nature of having implemented this whole methodology on RTL allows for some fine-grained vulnerability data that would allow for some smart and efficient CPU designs with fault tolerance and reliability in mind. Thank you very much for your time.
Hello, my name is Meirav Nitzan, and I'm a PM director at Synopsys, focusing on functional safety and security solutions. In this presentation, I will discuss the EDA viewpoint on automated solutions for safety and security. First, let's take a look at the issues discussed in previous presentations in this session. Serge Leef from DARPA talked about the AISS program and discussed the automation inclusion of scalable defense mechanisms into chip designs to enable security versus other economics optimization. Serge's challenge is to automate the security SoC design development. Bala Chavali from AMD talked about SoC functional safety and use cases. She also discussed standards and the dependability lifecycle. The challenge Bala is presenting is to standardize all aspects of dependable design data exchange across the supply chain. Reiley Jeyapaul from ARM Research presented PACE, which is a reliability analysis method for safety critical CPU design. The challenge Reiley presents is creating an innovative solution to ADF and application-based fit derate using existing EDA tools. Okay, I can say that EDA understands and accepts the challenge. From our perspective, creating new technologies and leveraging the existing solutions are here to create a holistic solution for semiconductor and system industry. We want to address safety, security, reliability, and time determinism of the product, and consider a holistic solution from software to silicon and everything in between. EDA industry works with the government and the academy on various initiatives that enable enhanced solutions for design automation and bring up new ideas by both sides. We also developed innovative solutions in collaboration with our customers based on their unique needs or interesting use cases where we see where we can automate the solution. Besides this, EDA industry participates in major standardization bodies to drive, understand, and implement new data exchange formats. Here are some examples. The ISO or SAE 21448, 21434, 26262, many Accelera initiatives such as the FUSA or the SAE-EDI, and the IEEE standardization such as the P2851. In all of this, the key is to come up with a holistic solution for safety and security from software to silicon. Before diving into the technical solution, let's understand the main goals of safety and security. The functional safety goal is to reduce the risk of hazard due to systematic failures during the design or random failures during operation to the acceptable minimum. What we need to consider during functional safety analysis is the integration of commercial safety compliant IPs in the SoC architecture. We need to think, how can my design fail due to insufficient planning or testing? And these are the systematic faults. And we need to consider, how can my design fail due to random faults, and come up with mitigation for it or safety mechanisms. In security, the goal is to reduce or eliminate the hazard due to intentional manipulation of the system functionality with malicious intent. Here, the considerations are, how do we integrate commercial security IPs in the SoC architecture with everything they bring with them? We need to think, how can my software fail due to malicious attacks? Or how can my hardware fail due to malicious hardware attacks? We also need to consider, how can someone insert Trojans to my design, or how can my design secrets get stolen? Looking at addressing the systematic failures, the key is, of course, a good and robust safety design flow. Synopsys offers solutions for all areas of product development: software analysis and testing, hardware design and verification, both for digital and analog, a wide IPs offering, test insertion, packaging, and manufacturing support tools. The key to avoid systematic faults or bugs in the design is to deploy best-in-class tools and methodologies with high level of confidence in their accuracy and competence. Synopsys tools are all ISO 26262 certified, and moreover, support best-in-class design and verification methodologies, such as low power, UVM, equivalence checking for synthesis, etc. The same level of confidence is required from the commercial IPs integrated into the SoC. So Synopsys IPs are ISO 26262 certified for ASIL B or D, and their development flow is ISO 9001 certified for quality management. The way to reduce the risk of random faults is to add safety mechanisms to the design. Here we show some examples of common safety mechanisms, such as core redundancy and temporal diversity, ECC memory protection, as well as monitors for voltage or temperature deviation from the specified working range. These can cause an unintentional behavior of the design. We would like to also point out the usage of ETPG for achieving zero defects at manufacturing of the chip, and the BIST capability or built-in self-test that enables key on or key off testing, or even periodic testing of the design. Synopsys provides automated solutions to insertion of these safety mechanisms in the design and addresses physical requirements of the safety mechanism implementation, such as physical separation of duplicate cores and freedom from interference. Of course, some of the safety mechanisms can be implemented in software. They are referred to as STL or software test library. They are normally a collection of tests which are run periodically or on demand. Their diagnostic coverage of random fault is part of the overall failure rate reduction metric. The quantitative metric offered by ISO 26262 for measuring design failure rate reduction is the FMEDA, or Failure Mode Effect Diagnostic Analysis. From our perspective, the FMEDA process is not only an after-the-fact analysis of the faults metric done on the final netlist, but rather a process that begins in the planning phase, helping to set up the technical safety requirements, safety mechanisms, and overall architecture, using estimated design metrics to compute the target ASIL. Then using early RTL and running the static analysis to get a more established estimate of the fault reduction metric, or safeness of registers, as well as best candidates for flip-flop hardening. When the verification test bench is mature, it can be used for fault injection simulation, including fault reduction, first in RTL, and then in gate level netlist to actually measure the diagnostic coverage of the safety mechanisms. Fault emulation can be used in case diagnostic coverage needs to be measured during software run with many cycles. The end result is the FMEDA with the accurate design data, such as number of transistors and sequential elements, such as flip-flops or ambits, and a measured diagnostic coverage of the safety mechanisms in the design. These two provide the final metric, which is the SPFM, or single point fault metric, the LFM, the latent fault metric, and PMHF, the probabilistic metric of random hardware faults. The security solution relies on the base flow of design and verification as shown before. However, it adds special considerations on top of this basic reliable flow I presented previously. On the software side, we add code analysis for software integrity, focusing on security of third-party software, security testing, such as protocol fuzzing, and virtual prototyping for secure software development with optional fault injection for testing the software resilience to design faults. On the IP side, Synopsys provides secure IP cores that perform security functions on a semiconductor. Things like root of trust, true random number generator, and so on. On the digital design side, Synopsys has various stages of support for security in digital design. Things like PPA analysis for differential power analysis, security register infrastructure, beneficial code insertion, with automated capabilities like dual-core lockstep and triple modular redundancy, programmable rule checks and security rule checks that are available both in the design side and the verification side. In verification, we use solutions for tracking secure data and data leakage checks, fault injection and test plan validation with a security test library. And emulation for fault and power analysis, as well as prototyping suites, are the final stage of analysis before coming up with a final tapeout. Creating trust that the system is behaving as intended needs to be done during various levels of operation. Protecting the system while it's offline, protecting it during power up, or protecting at runtime. In order to address all these stages of protection, it is important to create a secure area, a trusted execution environment to allow for secure execution and secure handling of assets, such as storage, and all of this based on strong cryptography. The specifics of the security solutions are influenced by the specific application of the design, the threat profile, and so on. Here we are depicting a neural network SOC diagram example. The protection of the AI systems, their data, and their communication is, of course, critical for users' safety and privacy, as well as for protecting business investment. For this application example, security needs to include overall SOC protection functions, such as secure bootstrap, to establish that the software or firmware of the product is intact. Key management, which is another very important security function. The secret key material should reside inside a hardware root of trust. Many neural network applications operate on large data sets that can often have significant privacy concerns associated with them. So protecting large data in memory, such as DRAM, is essential. Communication between edge devices and the cloud needs to be secure and authenticated so that data is only being downloaded to devices that are authorized to receive it. And also integrity is absolutely key. Model poisoning and Trojans in the models make end-to-end integrity of the input data and models crucial to protecting the system from adversarial corruption. Let's talk a little bit about security verification. The starting point in the analysis of security intent and the way to verify it is by looking at common weakness enumeration, or CWE, which is a community developed list of software and hardware weakness types. It serves as a common language and also as a measuring stick for security tools, as well as a baseline for weakness identification, mitigation, and prevention efforts. Security-driven verification takes into consideration existing knowledge base, such as vulnerability databases, and security-specific applications of static and dynamic tools to come up with full coverage of the security verification plan. As shown here, virtual prototyping is used for early architecture exploration and software development for security. Static analysis technology checks for security rules derived from those CWEs or out-of-threat resources, as well as quantitative analysis such as cyclomatic complexity. This one measures the level of complexity of a flow graph and hence its vulnerability level. Formal applications check for data leakage and prove data integrity or provide a counterproof. Fault simulation is used to check the security sensitive signals and mimic malicious fault attacks and their effect on the design behavior. Emulation platforms enable software countermeasure testing, as well as side channel attacks at the system level. The implementation solution flow starts from early PPA or power performance and area analysis to identify vulnerabilities to attacks, such as the differential power analysis I mentioned before. During RTL development, automated tools can integrate registers to communicate with the security infrastructure or address test mode access controls to support security and avoid a security breach in test mode. Synthesis of security design needs to avoid optimizing away redundancies, and this is similar to safety-aware synthesis. It also needs to support features like watermarking, obfuscation, and logic locking. Place and route tools have special consideration for placement solutions which prevent security risks, such as malicious implants. And they can add smart metal fill to resist optical probing. All this needs to be done while maintaining the target timing and power requirements of the design. Serge Leef presented DARPA's automatic implementation of secure silicon, or AISS program, to address the industry's need for mitigating persistent and increasing security threats against the hardware designs. Synopsys and Northrop were awarded prime contracts for providing solutions for this program. Synopsys is creating a tool flow that automates security hardening, which does not require specialized security expertise, while enabling application-specific trade-offs between security strength and other design considerations, as we talked about, such as performance, area, and power. The combination of the traditional design and verification offering in this flow, plus new and enhanced versions of current tools, mitigate concerns of an untrusted supply chain, such as malicious insertions of extra devices, preventing an unauthorized device from operating, and tracking devices through their life cycle, reporting vulnerabilities in the design prior to manufacturing, and when deployed in the field, enable secure execution of confidential operations, such as encryption, protection of secrets in the device, such as private keys, and so on. In general, this program provides levels of defense appropriate to the specific threat. Another aspect is the IPs. In the ASS approach, SOCs are composed of configurable IPs, which are maintained in a repository that maintains their integrity. Devices that can prove their authenticity are registers with a cloud-based asset manager, permitting various types of tracking and analysis. This tool flow enables the designers to quickly consider multiple system architectures that meet their design and security intent before making final architecture decisions. So far, we have talked about safety and security as two completely separate design challenges. However, in reality, and as noted in Bala's presentation, they greatly affect each other. The P2851 initiative in IEEE is chartered with creating a standard for functional safety data format for interoperability within the dependability lifecycle. The safety security alignment is one of the topics covered in this standard. Basically, the approach is to align safety and security requirements during the architectural phase and analyze the effect of the technical requirements from each discipline on the other one. Based on that, requirements may change, may be enhanced, or may be completely removed. So to summarize, EDA industry has been rising up to the challenge and providing solutions for safety and security. The focus is on holistic solutions that spans from architecture to silicon and considering software products. The existing tools and technologies are, of course, leveraged, and plus we add enhancements on top of them to address the unique challenges of safety and security in the design, verification, and the implementation processes. And participating in the standardization effort and cross-industry initiatives helps EDA and our customers create innovative, collaborative solutions that benefit all the players in the supply chain. I would now like to conclude my presentation by thanking the audience for listening to this tutorial and thank the esteemed safety and security experts who presented here their work and share their invaluable expertise with us. They are Serge Leef from DARPA, Bala Chavali from AMD, and Reiley Jeyapaul from ARM Research. Thank you all. Now we will switch to the live Q&A session. If you have any question on any of the presentations you heard in this tutorial, please raise them now.
Thank you, everybody, for listening in to this pretty long session. I hope it was beneficial and that you've learned some things from it. During the various presentations, there were a few questions that I captured. Actually, some of them were already answered, but let's go quickly over them again. The first question was to Serge. Can you explain how a security module will protect against each of the threat vectors you have identified? Serge, would you like to repeat the answer you gave in the chat?
Yeah, sure. So there are the four attack surfaces that I mentioned. There are strategies, and those strategies are implemented in the security engine in a scalable way. So on supply chain side of defenses, this involves a scalable puff that is root of the trust, and then everything else is built up around it. It has key store, it has silicon odometers, it has ability to trigger logic, deobfuscation, decryption. It also can communicate with off-chip infrastructure on the cloud for purposes of enrollment, authentication, provisioning, and others. It is scalable, so it can be made very small or it can be made very large. That obviously drives the key lengths and security implications of that. The second attack surface, reverse engineering, we're basically using a layered set of logic obfuscation, logic locking, logic encryption mechanisms in the security engine controls, and so that's also scaled in terms of size and invasiveness relative to the security objectives. For side channel attacks, the security engine manages the degrees of emissions that are observable from outside the chip during execution. And so here, we have several strategies that are implemented, ranging from matching active and inactive gates to reduce the emission, to cancel out emissions, introduction of random noise to mask the emissions, and then doing basically asynchronous cryptography to completely mask any emissions. Lastly, for the malicious hardware, or sometimes referred to as hardware Trojans. We have runtime Trojan detection system that monitors execution and movement of memory mapped I/O on the buses, and basically looks for potential triggers of Trojans. There's more that can be done on that attack surface as well. And so it is intended that the security module is programmable with more rules that can be uploaded to it if new vulnerabilities are discovered. And at least the original vision of the program also had some embedded FPGA in the security module that could facilitate hardware upgrades for attack vectors that are not yet anticipated.
Thanks, Serge. The second question was about security certification programs that you are aware of in the chip level or system level or firmware. Can you address that?
Yeah, I can only comment on the chip level ones because I'm directly involved in those. And I am in conversations with NIST at this point. NIST is like National Institute for Standards and Technologies at the relatively early stages and thinking about how they should be involved and what they should be looking to standardize and certify. And so far I've had two educational sessions with NIST and Department of Commerce to kind of bring them up to speed on what all the dynamics are at the chip level, what are the interfaces, what are the standards opportunities, and so on. But at this point, to my knowledge, at the chip level, there is nothing in place. The only usable standard that the security systems on chip would utilize at this point is likely to be intelligent JTAG.
I actually chatted with our software expert during this session, and he told me that there is some certification on software side that is the UL 2900 series. But I guess this is for big systems and not for the SOC level.
Yeah, I can only speak for the chips side. So at DARPA, we have 3 program managers basically that focus on security issue, and I have a peer that focuses on board level stuff, and then at system and software area, it's a different part of DARPA called I2O, and then there's another PM that has historically focused on hardware software interface or firmware. So there's activity in all of these areas, but what I'm responsible for is the chip level stuff.
Thank you very much, Serge. If anyone else has a question for Serge, please speak up now or raise your hand. Okay, we also had a question for Bala during the session. Bala, the question was, how do you apply the automotive standardization or all the design efforts to other domains such as data centers or industrial, etc.?
Yeah, generally automotive does have a lot of different standards. The same is not true for server data center. Although there are quite a lot of overlap when you look at the RAS and functional safety. And so I think one of the questions was, do you think we need similar standards? And I think having similar standards, at least covering the differences, would be it would be a good start, and it would be very helpful. And the main reason is because right now most of the server or the data center side, they do rely upon sort of the end application, and it tends to be very different from one customer to the other customer. And so I think it's nice because all of them have different requirements, but I think standardization of some of the base feature set would be very helpful. And on the reliability side, right, there are a few standards on reliability, but also, as you, Meirav, and myself, as we are part of the P2581, and as well as, the Accelera working group, we are driving, getting that same feature set or the same base parameters into the standard so that we can have the same common terminology that we all can talk about and use when we're discussing with customers.
Thanks a lot, Bala. Is there any other question for Bala from the audience? Balaji, you want to?
Yeah, I had a follow-up question. So safety element out of context is where has been very successful in automotive, right? And there are goods and bads of it. The goods is, yeah, you're decoupled from the requirements of the full ecosystem, so you can develop and scale better. But again, in the server domain, I think it's more custom, so it's not safety element out of context from what I can see, right? Is that a I mean, so I think we lose out on scalability. So I just wanted to understand your thoughts on that. I mean, because you'll have to tweak your solutions per customer, and then challenges there.
I think it has similar challenges to automotive, right? When automotive sort of started off, each and every market is different, whether you look at braking on one side or now you look at AD or you look at ADAS, there is something specific. And even in automotive, you sort of have your high end, mid, and low. And the same is true even on the server side. So we have to do something similar to safety element out of context for the data center and server side as well, because we won't be able to have one standard per customer. At the same time, we won't be able to have one that could apply to all. So we have to go find out what is that base set of features and base set of requirements that are there across everybody. And something like fit is something that all of them have, right? So we need to find out what that base is and use that to drive up a standard saying that these are the parameters. Now the numbers, whether it is in functional safety, FTTI, which is one number could be 10 milliseconds, 100 milliseconds, 500 milliseconds. So there would be some parameters that could vary across all the different customers. So we got to find that, the base set and something that we can make sure that would work across all the different customers and all the different sites, whether it's from low all the way up to high end.
Yeah, that's an interesting point, actually. Yeah, because there would be common requirements for sure. Yeah, so I think maybe I'm not aware of the domain very well, so I'm not sure that the term safety element out of context is really used in the.
Oh, it's not. I'm sort of using it because functional safety, coming from functional safety world, you're very used to it, right? Now they don't have that. I'm just saying we need a serverization of that word and something that we can say, we'll be able to apply for those guys, but not probably safety element out of context.
Great, awesome. Thank you.
Thanks a lot, Bala. That was very interesting. I actually had a question for Reiley. During your presentation, I noticed that you, basically it's all about defining architectural vulnerability factor, and you use some tests for that. And those tests really define the time when the data is active and changing and when it is not, or when it is safe. What's your level of confidence that what you measure in your own IP level test is what really applies to the application layer? Because maybe, metric or statistics is a bit different at the application level.
So you're trying to ask about if something is measured vulnerable in our metric, is it actually vulnerable at the system level?
Yes. What's the correlation between them? I would say. There are limitations to this.
I mean, like that, as I mentioned, what we are measuring is an upper bound, because we do not consider error propagation, and we do not consider error propagation both in the hardware as well as in the software. So there are software masking effects that can happen, that data that is consumed, either erroneous or non-erroneous, could be discarded and not result in an error seen from the system level. So that level of analysis is not part of the model that we have, and it is really difficult to do that kind of an analysis. On the other hand, what we did is in our experiments, we did compare against exhaustive fault injection, wherein exhaustive fault injection does consider error propagation, both in the hardware and in the software. And therefore, because we were able to correlate these two metrics, and the graphs actually show the numbers wherein we have exhaustive fault injection in the bottom and our AVF numbers in the top. And we see that over time, temporally speaking, the AVF numbers do correlate very well. And we see correlation percentage of around 80% in some instances for some benchmarks. And we've compared this for not just one benchmark, but for a few benchmarks, at least 5 benchmarks in the MI bench suite. So, so we are confident about this upper bound that we have estimated, but you cannot translate our numbers to exact fit numbers. That is, yes, that is a limitation. We propose this as a mechanism for reliability analysis that would help designers in evaluating vulnerable blocks or non-vulnerable blocks, and focus their efforts on targeted fault injection to understand exact vulnerabilities or derive exact metrics, and also to optimize for to divert efforts for optimization on specific blocks based on this.
Excellent. So this is how people should take your proposal, not as a finite answer about AVF, but rather as guidance.
Yes.
Okay, thanks a lot. And your paper was part of ARTS 2021, I understand.
Yes.
So the full paper can be found there, and there was a link
on the slides also.
Yeah. So anybody who's interested in diving more into this topic can find it in the link that was provided in the slides or in this chat. Is there any other question to any of the panelists from the audience?
So, sorry, I had a follow-up question for you, Meirav. Sorry.
Okay.
It was, I think, along the lines of what you'd asked Reiley. So I think, yeah, so what we estimate for benchmarks and how representative is that for final application, right? I think you had in your slides as well fault injection and other techniques. So there's many ways to calculate AVF, right? We really can't do this for the end application. It's really expensive. So how do you, how does Synopsys try to address this? I think I'm trying to repost the question, a different methodology that Synopsys has.
So clearly pure fault injection is not the way to measure AVF. What we are trying to do is to use some statistical analysis of observability and controllability of a certain register to get some initial information about this. And actually there was a paper published by ARM and Synopsys on combining this statistical analysis and fault injection done by Gani Kanawati. You can probably access this information. It showed the correlation between the statistical analysis, which showed close to 0 probability of propagation from that register, and the fault injection results, which also showed 0 propagation. But you know, all those 20% probability or 30% probability is, of course, harder to prove. So this is something we're still exploring. How can we make our fault injection smarter? And definitely your input about the payload and the enabler is something we should be considering in our fault injection. That is a very smart point we're gonna take into account.
Thank you.
Okay, very good discussion. Anyone else wants to raise any question?
Quick question then, Meirav. So does that mean you are able to do it for a specific I guess, use case, or are you still doing injection, diverted towards a single, bit or single array or a single location?
So the fault injection simulation relies on use cases or tests, same as in the functional verification. The statistical analysis of observability and controllability is not relying on any test bench. It's just an analysis of the RTL itself or netlist. Combining the two is the challenge, to make a coherent picture that comes from two different sources. And hopefully these two would help speed up the decision and the simulation cycles.
Okay, thank you.
Okay. Again, I will ask if anybody else has any question. If not, thank you very much, Serge, Bala, Reiley. It was an excellent session. I hope everybody enjoyed it as much as I did, and enjoy the rest of your DVCon.
Thank you very much.
Thank you.